So for attendees who are currently attending, feel free to post in the chat or Discord. I'll keep an eye on those for questions. This will be an interactive presentation. And if you're following along in the future on YouTube or whatever video format, feel free to pause the video and try to answer the audience questions that I'll be presenting today. So, again, let's go ahead and get started here. We're going to be talking about the strategy design pattern. This is a beginner level talk here for the strategy pattern, but I will find, or hopefully, one of the goals will be for understanding where to apply the strategy pattern, as that's sort of the important part. So, we're going to look at some code, some examples, and again, just understand the trade off with these design patterns. Again, design patterns are never perfect, but understanding which ones are available, and so to speak, which ones are in your toolbox can help you improve your software and improve your software development workflows. So that's the hope, at least. So my primary role is I'm a teaching professor at Northeastern University. So I love doing teaching and various courses and systems and graphics and so on. I do research in graphics and systems as well. I do consulting and technical training, usually in modern C++. So you can find out more about that as well as on my YouTube channel, the kind of stuff that I'm programming these days. So feel free to enjoy those resources beyond this talk. The code for today's talk will be available on GitHub. It's already posted on this link if you'd like to follow along or download it. They're mostly toy examples, but they do compile, they do run, and they might be insightful for you to work and play around with. And I'd encourage you to treat these sessions as interactively as possible and to play. That's how you learn here. So again, here's the abstract that brought you to the session. So if you want to pause and see what you're going to learn here, that's the basic idea here. So we'll go ahead and move forward here. And not to surprise you too much, but I actually want to start off with a little bit of a software interview here today. And I think this is a good place for us to start and even think about some of the software that we design here. So I'll monitor the chat if you have input, but otherwise you can also just think if you want to sit back and relax for these different questions here. And first and foremost, I wonder if folks have sat through a software engineering experience. I'm sure many of you have if you're attending this conference, and maybe some of you who are watching this in the future will be preparing for something of this matter. But I wonder how many of you have ever described this to a colleague or maybe a partner or a friend, just what goes on in the software engineering process. And if you have, feel free to post in the chat or you can comment below what your experience was. Hopefully, it was a good one. I'll just keep an eye out for those responses. Um, but if you have gone through this process here, very likely you've explained how the typical interview goes. So usually you're answering some questions, maybe on a phone screening, maybe several rounds of technical coding in front of other folks, or maybe on a desktop while they watch you type code, or maybe you've even done some take-home tests, for instance, for a company, or maybe even a presentation, or maybe something else beyond these exercises here. And my personal experience has involved, as far as doing software development, this whiteboard here, where most frequently you'll end up writing code on a physical whiteboard, or again, maybe on a terminal online doing screen share like we're doing now virtually. And that's just very common for going through the software process here. So I wanted to start off, even though we're talking about the strategy pattern, about looking at some software interview questions. And maybe we'll uncover something about them or the design or the thinking or thought process that goes into one of these. I won't call them a toy problem because they are valuable for how you think or train yourself to think. But maybe there is something in how we think about designing these particular algorithms. And we want to think about if they're very constrained or maybe if they're part of a family of algorithms where we can maybe reuse some of the code or not. So, anyways, where I've started here is by gathering, one of the top interview questions. I think it's number 267 on this list because I thought it was interesting. But I thought it was a good one for the level of this talk here, where you might have a prompt such as the following, where you want to find the duplicate number. So given an array of integers, nums here containing n plus 1 integers, where each integer is in the range of 1 to n inclusive. There's only one repeated number in this numbers array, and you want to return that repeated number. So you must solve the problem without modifying the array that's passed in here, and uses only constant extra space. So again, I'll pause for a few moments here, or you can pause the video if you're watching this in the future. Just think about how you would solve this problem. And for those currently online, feel free to pop something in the chat if you have a solution. I'll keep an eye out for that. All right. And I see some folks are thinking, maybe you've thought about it for a little bit. Maybe you've perused some of the standard template library to solve this problem that can help you, or maybe you've dove in and paused here for a moment and have tried to solve this. But regardless, this is a nice sort of question to start thinking about here for our algorithmic design and how we might approach this particular problem. What's sort of a methodology that we might use here? So, my question to follow up with that, regardless of whatever algorithm that you're thinking about, is to think about, first and foremost, can you find one way to solve this problem? But secondly, can you think of a second way to solve this problem? Are there two such solutions that you could find for finding a duplicate number? And that itself is kind of an interesting exercise if you're practicing, for some software interview and thinking about different algorithms or approaches. There's rarely one approach to solving a problem in software engineering. Again, this is why this is a sort of design patterns talk. It's one of many. So it's interesting to just think about or even challenge yourself to figure out what the solution is. Maybe you want to think about the most efficient, maybe you want to think about the least efficient solution as well, which is also a fun way to think about things. So, something I was advised when I was interviewing for software engineering jobs is, first and foremost, could you come up with a solution, even if it's a brute force solution? And then you could kind of think of something better. And I think that's still true when we're developing software, that sometimes you just need to get something that works first, and then you can iterate on it and improve on that solution. I don't think there's any problem with that. So, if I approach this problem for finding a duplicate number in a vector, let's start with what I would call a brute force strategy. Again, I'm going to break some of the or maybe I'll use more than constant extra space. But we could proceed with that again, just to get some solution so we could move forward. And then the second thing that I think about when I'm designing algorithms or implementing code is, what are the probing questions around this? Meaning, what's the size of the array? Do we know if it's really large? Is it really small? What are the data types? Again, we have integers and so on. So those are some of the things that we could think of. Okay, so before I reveal my first brute force solution from the chat on Discord, I'll go ahead and read off. We've got one from Imran. We could sum the numbers and compare with the sum of numbers 1 minus n. There's a known math formula for that. Okay, very cool, very cool. Actually, a solution I hadn't thought of there. I have one other audience member type in using bit masks. Okay, so I can maybe figure out where something is repeated or a set type of data structure here, if that's what you mean by bit mask, because we sort of know the range from 1 to n. That's going to be part of this. Yeah, and 1 minus n equals 1 to n. Okay, so we're getting some formulas in here. Great, great. All right, so let's start with the brute force. Then we're getting some clever solutions here from the audience, which is great. But I would say a pretty brute force solution would be to, make a copy of the vector, sort it, which could take n log n. Maybe there's some more clever sorts that we can do on integers, but let's just say we just use some comparison sort, and then we iterate through the copied vector, and we should find the duplicate number, right? There should be an adjacent element that is the same, right? So as we're iterating through all n elements, the n plus 1th element will be equal to the nth element, right? If we're sort of checking who our neighbor is. Okay, so that would be one sort of brute force way to find this duplicate number here. Okay, so I think that's reasonable. Are we done? Probably not, right? There was our constraints here. And there's even a follow up to this problem to make it more interesting for how we can prove that we have at least one duplicate number that exists in the numbers. So again, thinking about our theory stuff. And can we solve the problem in linear runtime complexity? Okay, so getting a little bit better here, making sure that all of our data structures are doing something with linear time and not n log n, which, if we're using a comparison sort, that eliminates things. So maybe we can choose a better sort here. So, anyways, this suggests that, we should have some optimal strategy for solving this problem. And maybe there's only one strategy for getting an optimal answer here, right? Something in linear time. Maybe that's something I can actually prove here. And then, as Adam was mentioning in the chat here, yeah, this is the pigeonhole principle for proving it, right? So we've got our domain or our range of numbers here containing n plus one numbers, and then this range of just one to n. So of course we can only have one value in all of the pigeonholes here, except for one, of course, will be duplicated. Okay, the basic idea there. Great. So, to kind of move forward with this problem, there's many possible other algorithms. Maybe you came up with some of these. Again, I said it's interesting if you can come up with at least two sometimes for these problems. But maybe we just iterate through the numbers and store each value in a unordered set. So again, some unordered set or a bit set or bit mask, as was mentioned, different data structures in different languages. And then we could just test for membership before adding. And again, if we have a unordered set, this should be constant time or so on average to add something. And using, well, we could pre-allocate the space here. So it's a little bit what the constant extra space means. Well, we'd use n space there. Okay, so maybe we're not quite there with this answer. And then maybe some of you were more inclined to use like a multi-set. Again, pretty much the same thing as unordered set, but you have a count function here, so you can actually just check what that count is for all of the elements that you're adding. That would totally be fine. We could do something like, again, copying the vector. Well, that's going to take, O of n time. Or maybe, since everything's contiguous, we could sort of do that in one operation here. So we got to think about that a little bit. But then there's radix sort or counting sort or some sorts that allow us to sort integers in linear time, which is great. And then you do have an adjacent find algorithm, which will take care of that iteration effectively that we're doing here, looking for, do you have a neighbor that's the same? And maybe somebody's done a clever implementation of that. But again, these are just some things in the C++ library. There is a pretty optimal algorithm for cycle detection that you can use. This one's kind of fun here. So I'll leave the link here for the solution here, where you can basically treat this as a cycle detection problem and chase the indices. This is known as Floyd's cycle detection algorithm, or the tortoise and the hare, and basically see if you repeat a number while you're moving effectively two pointers through these indices. So that helps us use only constant space, because we just need to effectively look through the numbers array. And we can do this in linear time here, because we're just, again, bumping pointers, so to speak, or in this case, indices through our array. So again, lots of different solutions to this problem here, and some also from our audience, which is very neat here. So again, I would encourage you to try this and then to try to write the solution. And you can look at Floyd's cycle detection, which is kind of neat here. So what's interesting for this type of problem here is, we're striving for some sort of optimal solution. And ultimately, we probably are going to land on one algorithm that works particularly well for solving this problem here, for finding the duplicate number. Now, again, we could ask some probing questions and figure out, does this work for all data types, or other sorts of things here. So, this is a pretty constrained algorithm. We can prove something about it, for finding duplicates here. Although there might be some variation here, but it got us thinking, hopefully, our brains working on different solutions here. So let's explore just a little bit more some of these problems here that we often work on in computer science. I'm going to start with sort. That's going to be sort of our working problem set for this talk. And I know sort is used all over the place. Right? The truth is, you learn sorting algorithms in university or textbooks or talks like this because they're a pretty understandable problem, right? We know what the objective is going to be to sort something in ascending or descending order. But there are many different strategies for doing this. Again, thinking about partitioning data or merging data and so on. And this actually will work nicely with strategy pattern, although we'll look at a few examples with strategy here. So, again, we can start thinking about working with our data in different ways. Again, you can see all the different sort algorithms. Again, there's hundreds or thousands, and new sorting algorithms always being invented, which is kind of neat here. And again, if I just ask you to sort n integers and to do it as fast as possible, I could ask you the same question here. You're welcome to sort of pause or reflect on, which algorithms you think are best, or you can cheat and look at this sheet here, actually see the space and time complexity that might work here. And just think about, what you come up with. What comes to mind when you hear sort? Probably something like, quick sort might come to mind. Again, accounting sort or arraytic sort or different options. And maybe even insertion sort comes up in mind that you remember those from your algorithms class or whatever. Or maybe you just remember the dot sort function that you're going to call in the C++ standard library. And that's also totally fine. Maybe we're not sure exactly what that sort is, but do know we have it available here. But what is interesting is that all of these algorithms have different trade offs associated with them. Okay. And you might also come up with, again, for our interview strategy, some sort of different probing question, thinking about maybe what kind of data are we sorting? Do we want it to be ascending or descending? How large is this collection of things that we're trying to sort? Those could all be things that you're thinking about. So, as a quick aside here, I'm going to bring it to C++ in a moment. And I remember this specifically from Java because this was sort of interesting in my university studies when I was thinking about, well, if I'm going to sort something, if I go back here, even back to the table, right, we just default to something like a comparison sort where there's n log n complexity. Okay. And we always sort of figured out that was the best in algorithms or whatever. But then you take your systems class and you start thinking about things a little bit and actually measuring. And you find out, like the folks did in the Java standard library and in the C++ standard library, which we'll look at in two slides here in a moment, that there's something really, really interesting here if you actually dive into the sort here. One, you start to see that there are certain specializations for the different data types here. So again, they are asking, some of those probing questions of how do I sort a byte array versus a char array and different sorts of data sets. Um, and the second thing that's really interesting is you actually go into the implementation here. You'll see that this comment says use an insertion sort on small arrays. Of course, if you just take the big O complexity for what it is, again, you know that, well, insertion sort is going to do some sort of, n squared, right? It's a comparison sort there. But of course, if you know if something's nearly sorted, then it might have a different complexity, or when we measure it, behave a little bit better. Or these sort of things like, does this algorithm allocate a lot of space, or can it do things in place, or is it stable? These sorts of things start to matter. So, anyways, they've sort of decided empirically, and I've seen these numbers change over the years. I think it used to be 47 or 43 at one point. Now it's 7 here for small arrays. That we should just use insertion sort or this sort of algorithm or strategy here when we have really small arrays. Okay, so that makes enough sense for me. And then maybe you use quick sort or some other thing for larger arrays. So interesting, we're making this sort of decision here. We have some actual condition and a branch here. And again, that's probably because of the locality. So again, these probing questions that you could ask if you're interviewing for a job are things like, how large is the collection? How large are the elements that we're sorting? Do they fit in a cache line? These sorts of interesting things that you'd want to know, right? If you know your data and understand your data, then you can solve the actual problem. You can choose or select the right algorithm as needed. So again, to bring this back to C++, we're at a C++ conference. And if you look at the actual C++ sort routines or some of the libraries or some of the implementations of the standard library, you will see also that there is some threshold value here. Okay, maybe it happens to be 16 for this particular data type, right? Something that maybe fits in a particular cache line here. Okay, so you have this threshold value here. And we could just check, if we're greater or less than the threshold, go one path or the other path. Okay, so this is kind of interesting to think about. And again, these sort of trade offs appear in many different places. So again, not just sorting, but in searching, right? Whether you should do linear scan or binary search or these types of things, or if it's worth the effort of sorting first to find something. Again, you can find all these sorts of examples. So again, it's not always black and white as our algorithms classes will teach you. And this is, usually there's some sort of intro sort. So you can look that up for C++. So, anyways, what's interesting with both those sorting algorithms and what we see here is that we're changing the behavior of what's actually done by branching. Right? We're using some condition, if, else, whatever, or we could use a switch statement, but to change the actual execution or behavior of our program. So, again, when we execute our programs, a reason for adding in this branching is, well, something might have changed here, right? We don't want to just take it for face value to sort, right? This is an actual maybe system that's running, right? Maybe you're working on a larger scale piece of software. It's not a tiny leak code problem, right? It's something that actually we're doing some work on. So what we might want to consider is, while our program is running, especially if it's a long running program like a video game that you're playing for hours or a server that's running 24/7, well, the workload is often changing. So we might want to consider what happens if we're sorting again different data sets as we have new data arriving on a server, for instance, of different capacities. We might want to consider again if some state has again changed in the application, maybe based off the user interaction. So again, in a gaming example, because I come from sort of gaming graphics background, maybe the artificial intelligence changes their pathfinding algorithm to be more passive, maybe adjusting to the user's skill level or some event in the game that happened. Again, you'd want to be able to change that, right? We would have some sort of branch, maybe if the player's doing very poorly the game, then change to a simpler algorithm that gives the player an advantage, right? That would be the idea. And then, of course, there's all other reasons, a bunch of other reasons we might want to change the behavior. Like, for instance, if the system has more or less resources, we might want to slow or speed something up. Or maybe we've just entered some sort of error state and we will actually want to do something else, right? These are all the different reasons why we're using, conditional statements here. So, at scale, again, being able to choose different algorithms or behaviors is going to be a advantage, right, for building better software. So, let's code this up. Let's write a sort. Again, we're going to stick with sort for now. And I'm just curious what folks think about this code, right? Maybe I've done a bunch of experiments. I'm a sorting expert. I've learned all these cool things: insertion sort, tim sort, merge sort, right? Interesting, variations of these problems. Um, and I mean, is this reasonable? What do folks think? I could write code like this to sort of sort based off of empirical measurements that I've done with different data types. May just let folks think about this for a little bit. Getting some folks typing in. Any answer is good. Again, if you're watching this virtually in the past, just pause the video and think about it for a few moments. No wrong answers here. Yeah, let's see. So I'm getting in from our users too many branches, but for first prototype to get strategy straight. Okay, yeah. Now software, of course, is definitely a evolutionary or iterative process here. So, this might be perfectly fine, right? We don't need to necessarily introduce lots of abstractions, especially if we don't know if this is the final product, for instance, right? We don't want to bind ourselves to an abstraction that's going to be hard to get rid of later on. Now we do have a lot of branches, which is kind of interesting. So we're branching around, right? If we're thinking about performance, our CPUs don't necessarily like that sometimes. Sometimes it's necessary, but sometimes that's what we have to do. So let's see. So I see one more person typing in the chat here. And it's too specific, may not work well for architectures. Yeah. So what happens if how I measure it on an x86 machine or an ARM machine or a PlayStation or these different things, right? Do these threshold values work? Maybe they all have different, or the same cache sizes and these different things. So yeah, we got to be really, really careful here with maybe this type of code here. So, this is getting to the point of, is this code maintainable? Is it reasonable? Okay, maybe if it's these four conditions, I can read this, I can debug this pretty well, I can look at it. I could probably run this through a profiler and see, very easily which functions getting hit and so on. So maybe it's reasonable at this level here. I'm seeing a few more answers coming in the chat. Yeah, let's think about it here. I'll make sure to read off the answers so our whole virtual audience knows what's going on. Oops, somebody's still thinking. So let me push this slide one more forward too, just to push my argument, I suppose. Here, that let's say that this uh, codes evolved over some time here. And we start adding, different threshold values. We're a little bit scared to modify this. That's a little bit of a magic number here. Somebody's saying in the chat, we could use variables for the threshold sizes for different architectures. Yeah, we're probably going to want to have some sort of state, right? Just having these magic numbers here, that's probably no good. So we at least want to encapsulate that. But easily we can see that this is getting out of control here. And maybe for sort, we're not going to be this specific, right? At 16, or I was just doubling the increments here. But you can imagine these types of things start showing up if you've ever looked at a code base with lots of different if def, preprocessor statements here. And a comment, yeah, we like the last branch. Just use quicksort. Maybe we just give up when our code starts looking like this. Just pick something. So, anyways, and I'm being pretty nice here, putting everything in one function here, right? So, I've looked at code bases that sometimes look like this. Maybe this is code we didn't write. Maybe it's auto generated. Maybe there is some sort of argument for it being optimal for a compiler or something, right? Where you have these giant switch tables or something. But, if anybody's got to read this where you actually unfold and implement the different algorithms, that's probably not great, right? To have all this state here. And again, maybe that state is consumed here, maybe it's accessing other global or local states. So we can get ourselves into trouble over time if we write our code like this. So I'll go back to this. This is what ChatGPT told me to do. Do something like this. Figure out a threshold, write the function for the algorithm, because functions are a great way to make our code more modular and so on. But my point also with this is also, we really need to understand some of these software principles or strategies so that when we get auto generated code too, we understand them. Because I couldn't get help here, enough help. So, anyways, let's look back at this example here, this line of thought with these different algorithms here. And another way to think about this, if I start writing my code like this, is, well, how testable is this? Am I writing one test per function here, one test per branch to make sure I get total coverage of my code? Those are some things that we want to think about. How am I measuring the performance? If I'm just testing maybe the algorithm, am I testing the algorithm with all these different branch conditions? So it gets a little bit tricky to test some of these things as we, complicate our code and add some complexity. So this is where some abstraction might actually help us. So again, looking at this code, this is of course not very testable. I would argue, it's going to be again pretty difficult here. So again, we might be able to get away with this in our program. I don't want to set a hard rule not to do this or never to use if statements or something like that. But again, if we start accumulating them and have lots of different but related algorithms, this is what we're going to find out the strategy is great for. Okay. So again, observe, we have a bunch of related algorithms here, our sorts, which are all, acting on, we could presume the same data, some vector or container that we want to actually sort. And that's the idea here. Okay. So we've got these conditions here where we want to, we want to be able to change behavior, right? That was the point of having the conditions here. If this is true, then, fall into this condition. And we want to be able to do this at runtime, right? As workloads change or different data sets come in. But again, we've got different algorithms to choose from. So how can we do better here? So the goals here for this talk, the rest of this talk, is to figure out how to maintain that same flexibility to choose the right algorithm. But we also want to manage that complexity. of our code. So whether that's at runtime or compile time, being able to choose the right uh, algorithm without the cost of, again, making our code very, very um, difficult to maintain later on. Okay, so perhaps we're going to find a way to organize our related algorithms. And again, if we have our algorithms well organized, usually that means it makes it easy to refactor our code to do experiments as well. Okay, so that's another part of managing the complexity, giving ourselves some freedom to be able to change and refactor our code pretty liberally. And it's also reasonable, I would say more than reasonable, that we want to be able to test our algorithms as well to make sure that there's an easy way to confirm it's either working or measure the performance as well. Okay, so let's work on this first goal here and maintain flexibility for choosing our algorithms. Okay, so, one mechanism that we can use is, well, we can start grouping up these related functions for doing our sorting here into objects. We could introduce inheritance here. Okay, so we could basically have different classes, maybe a sorting class here, and basically have everything be again part of a family, right? That's where the sort of term inheritance is coming from here. So let me advance here a little bit, right? Where we have some sort of base class and we derive new types from it. Okay, should be relatively familiar for folks, hopefully. And we want to do this in the context of a sorting problem. So let's say we have an interface here for our sorts on the top right of the screen here. And we basically want to implement these different sorts. So I'm going to have, insertion sort, bubble sort, quick sort, etc. That all have this common interface. And then ideally, I'll be able to, change the actual sort based off of this interface. Okay, so here is the basic idea. Again, with compiling C++ code from the code samples, here's our interface here. We want everything at line 7 to be able to sort. So we have a purely virtual function here. And then we implement our two sorts here from the interface, and then implement the actual insertion sort, the bubble sort, quick sort, etc. Okay, and then what you could do here, now that we have everything that's part of this common interface, again, insertion sort is a type of I sort, and a bubble sort is part of our interface here for I sorts. Now we can actually use, looking at the bottom right here, runtime polymorphism to select while our program's running and allocate different sorting algorithms as we need here. Okay. So again, what's being shown at line 24 is I'm just allocating some type of sort here and then choosing insertion sort, calling the sort, and then we can delete it or clean it up or whatever we need to do here. In fact, let's make that a little bit more modern. So, since we're at a premier C++ online, right, we should probably use a unique pointer or something here and allocate that way so we don't forget to, free our memory and so on. But you sort of get the point here that we're able to now select by just assigning our sorting algorithm to some value here. Okay. Now, a few notes on this. We are using inheritance here on runtime polymorphism. So basically, what's happening is when our program executes at line 27 here, it's going to call the appropriate sort based off of the actual type here. So again, runtime type polymorphism. And that has some overhead again for my performance-minded folks who might be jumping into this talk here, where there might be a level of indirection. Maybe it can get optimized out, maybe not. Again, it just kind of depends. So that is some cost we're paying here. The advantage is though that we are making sure that we are only able to assign to different sorts here: insertion sort, bubble sort, quick sort, etc., whatever inherits from our interface. So, we get some sort of type checking. We also, for other types here, and for sort, it's a pretty clean interface. But we are able to enforce this interface here, which might be of importance here. Okay. And if you're in the camp of you don't like object-oriented programming, good news. In C++, you can use lots of different paradigms. So you could, put a bunch of functions in a variant or something and make calls to those if you wanted to, again, sort of change your behavior to more of a functional style. That would also be possible. Again, you're still introducing the same layer of interaction, but if you don't want lots of objects showing up in your code, that's one other strategy. Okay. So, anyways, let's further just sort of organize our sort here function. Maybe we implement the generic sort here, and within this function here, shown between lines 23 and 34, we're still doing something pretty similar to what we had before. We've got our maybe threshold sizes where we can choose things, but now we've at least got these building blocks, which are interesting. The insertion, the bubble sort, quick sort, and so on, that we can start working with these actual objects. So we can see them as building blocks for implementing some other algorithms, like if you caught Tim sort or intro sort, like I introduced earlier, which is basically an insertion sort and a merge sort together. You could start implementing something which is interesting with these building blocks. We've also sort of improved some of our code in some sense of its maintainability, right? We've got these insertion objects in bubble, this object here for doing the different sorts, and they've got one job to act on data. So that's a nice sort of single responsibility principle. We're kind of breaking our program up and decoupling things a little bit. So again, this is pretty clean code here. We haven't gotten away from the branching yet. Um, so we need to think a little bit about that, but we do have this, generic sort function that we could call here. Okay. Okay. So now that we've, explored this idea here, I would say, we've got flexibility to choose our algorithms using the runtime polymorphism in as clean of a way as possible, right? We've taken out instead of functions, but now we've got objects that we can reassign. And again, maybe we can allocate those algorithms as we need. We just get a little bit more freedom here. Okay, so we've got more flexibility, I will argue here. But what about the complexity of our code? Okay, so again, thinking about how to manage this sort of complexity, it becomes pretty easy to add different sorting algorithms, right? They know exactly the interface which they're inheriting from, or should be, right? This interface here, and if there's different functions that we need to enforce, we can provide them in that interface, which tends to be a good thing. Okay, if you're adding something, you can see if it fits in that family. And again, we've sort of isolated all the sorts in their own hierarchy, again, which is kind of nice here. And but we do have to be a little bit careful with getting carried away with inheritance. Again, this is just sort of a general design thing. Again, it's not a hard and fast rule, but someone mentioned different architectures, right? Maybe we have insertion sort for x86 or ARM architectures or RISC or whatever that have different and neat instructions. And then we start building up, this other hierarchy here, that starts getting a deeper and deeper traversal. We do have to be a little bit careful here for our hierarchy. One gets too deep for the different levels of interaction, and as well as it's not really managing the complexity very well. Okay, that tends to be the case here. Okay, sorting, maybe we can get away with this, right? This is simple enough. I think that folks understand it, but we probably want to be careful once we start getting more than one level deep. Again, not a hard and fast rule, but something to keep an eye on. Maybe it's better if we just inherit everything from this one base class here. Okay, so again, we still have the separation of concerns for each of these algorithms doing their own one job here. Okay, so let's go ahead and continue forward here. And talk a little bit about the testability here. Okay, so have we improved things by wrapping things in their own object here? Well, with each implementation of our sort, we can test this relatively easily. So I've prepared, some basic unit tests here. And you can see, for each unit test, I just call into a different sorting algorithm, and then we can call those unit tests. Okay, this would fit very well and choose your very favorite framework, Google Test or C, or Catch, for instance, Catch 3 or Catch 2. And you could use one of those frameworks again, or one of the many frameworks to write unit tests like this. You can even start to parameterize these unit tests, perhaps with the different sorting algorithms, which again makes things very clean, very testable, as well as it becomes a little bit easier for test-driven design, for instance. So you can write that object with your new sorting algorithm that you invent, call sort on it, and you have a pretty clear expectation of what it's going to do, or you can test, right, if it is actually sorted. Okay. So, anyways, I think this is a big win for sort of test driven development. Okay, so if we review some of these goals here, it looks like it's just as simple as that for writing, better code. We're going to remove related algorithms into some inheritance structure. Okay, that's going to enforce the types for us. So for the type safety, you can only call or use or assign to different types of sort. The structure is otherwise pretty clear if we keep our hierarchies not too nested, but we do have to be a little bit careful. Inheritance sometimes lets us, go a little bit wild. But there is the actual pattern that's leveraging this idea, and that is well into the talk strategy design pattern. That's using this exact idea. So you can kind of see how we got to this formulation here for the strategy. So I'd like to present one more example and formally what the strategy design pattern is. So what is the strategy design pattern? Well, it's the strategy pattern, which also goes by this other name as policy pattern, or that's something sort of related. It's a behavioral software design pattern that enables selecting an algorithm at runtime. Instead of implementing a single algorithm directly, code receives runtime instructions as to which in a family of algorithms to use. Okay. Again, we're going to enable selecting an algorithm at runtime, again, with a little bit more flexibility by having actual objects. I will add that this adds a lot of other interesting use cases because maybe you're loading these algorithms from a shared library, for instance. So it's not just the code that is, fixed when you compile in your program. Okay, at least in the instances where you're able to do this runtime selection. The policy pattern usually works with compile time stuff, which we'll touch on. But we get a lot of flexibility here. And again, the idea is that usually you wrap things in related or a family of algorithms. Okay. So when to use the strategy design pattern, I'll give a few highlights, right? We looked at sorts. That's an obvious one. But you can think of anywhere where you have multiple algorithms to choose from. Compression algorithms, you might want to choose a lossy versus a non-lossy compression algorithm. If you're exporting data, are you writing out to raw text, JSON, XML, YAML, whatever it might be? Again, you might want to have different algorithms or strategies for doing that. Different graph traversals, whether that is like in the gaming example of pathfinding or pre-order, post-order, in-order traversals, or maybe Dijkstra's shortest path. Again, you have a wide a family of algorithms that fall in these categories. But also when you want to, that gives us kind of a hint for which things we should kind of group together to prepare for the strategy pattern. But anytime you have some software where maybe you don't want to have to redeploy, and again, you want your software to adapt to different scenarios, right? Maybe you have a strategy for how to do sales when it's the holiday or when there's a discount, for instance. Again, you can have these different sort of things that don't require you to rebuild, redeploy your software. Okay. As I already mentioned, for making testing easier, again, versus just having all of the code and all of the state out in the open, wrapping things up into objects and doing a test driven development style thing can be an advantage. And then the fourth case is usually if you find yourself with lots of if statements and you're beyond that sort of prototyping phase, that's where you might want to consider wrapping things into different objects. Okay. If you're seeing lots of different behaviors being collected there. Okay, so let's look at some strategy patterns in the wild here, just again, so we can understand, where we could actually use this. Again, I'll give you another exercise here. And I wonder, have folks seen in the C++ standard library anywhere where strategy is used? Anywhere come to mind to folks? If you open up CPP reference and I don't know, click on most anything, maybe you'll find strategy. What have folks found? Here we got a few folks typing in. Because we kind of know what it is, right? Where are places where we can choose different algorithms or behaviors at runtime? We see one coming in from John Fleet, the standard vector plus allocators. Yes, yes, right. So we see this a lot in our containers where you have a choice to make about, well, different strategies that we might use. Execution policies for threads. Yep, I will count that. Using lambdas for custom sorting comparators, great. All right. Looks like folks looked through my slides already. How did you get a hold of those? All right. So, execution policies, as was mentioned here, right, where you can choose how some algorithm's going to perform in parallel or not. Again, it's got the word policy in it. So, again, this sort of policy based design is a good hint here. Anywhere where you have comparators, right, where you're changing the behavior of, well, how you're doing, finding a min or a max element or sorting something. Allocators, as mentioned, also you're choosing which allocator you're going to use with your vectors when you set these up at compile time. So those are all great ones. Yeah. And I'm sure there are many other places here. I'll keep an eye on the chat as folks type in others and share. On comment just coming in is the use in STL compile time? Well, yeah, anywhere where you're using these templates, that is happening at compile time. Correct. Yeah, um, we are setting that up here. Now, for our actual functions here, like if I have something like reduced, or even let's see, the sort heap here, where I'm passing in a comparator here, right? That is something that I can change when my actual program is running, right? I can have different instances of the sort here. So I can have some dynamic behavior, right? I could allocate this in some sort of function, stood function, and then call into something else here. Okay, so you still have the runtime. You can get the runtime behavior. Yep. Now the advantage. Let's go to the next slide here. The sort of policy-based design, right? If you're doing things within templates, which this was popularized in the modern C++ design book, as the wiki is going to tell you, is to use a lot of these sort of selecting your strategies at compile time, as folks were mentioned, right? Because then you know exactly this can be one way to get rid of some of the indirection and performance issues, right? And again, usually in C++, we're choosing for performance. Okay. So there we go. So another little exercise here. We'll do just this one here, and I'll keep moving us along. But if I showed you this application here, which is the tool the GNU image editor. I mean, if you just looked at this for a moment, could you see maybe where are some cases where you could use the strategy pattern? Where would this benefit? Do you see anything here? Again, and maybe you haven't used these tools for doing painting, but it's a painting tool or working with images. But this is sort of an interesting exercise to just look at some software and think about where could I maybe see a family of algorithms and maybe have some sort of strategy. And someone's mentioning Adam, the tool selection. Yeah, absolutely. Right, where I see the different tools here that I'm using. Right, because all of these are basically the tools that I'm using when I click my cursor to figure out do I flood fill or paint or use the spray can. And then the UI tab itself, yeah, sure. Setting up different behaviors. I mean, for a lot of these different things here. Let me advance this one more. I mean, there's a ton here. I mean, this is a great candidate for many different strategy. I mean, there's other patterns that we could use here, but I mean, let's think about one flood fill, for instance, which is again something that you could set up as a strategy. And even within flood fill, there are different algorithms, fill scan and so on, that you could use. Even for like moving stuff around, you just want to click and move, but you want a different you just want to do the action or a strategy for moving something around. Are you moving the actively selected object, the whole layer, or so on? Okay, and of course the different brushes could be a potential sort of strategy. Now we could also think about these brushes depending on how they're designed with other patterns like decorators and stuff. We could use strategy a lot for the tools here. So some other ideas here, right, where we find strategy in the wild, things like the command line applications, right, anywhere where you're putting in. This is for FF MPEG, just because when I've used it, it has tons and tons of arguments. But when you think about the different encoders or decoders that you're selecting, again, just another example. These sort of falling sands games, if you've ever seen them, where you're every pixel is a different particle type, right? It's fire, water, lava, sand, and so on. Again, you might want a different strategy for how those interact with the nearby uh, particles, right? The neighbors, right? The fire goes through the sand and so on. Um, so just another example here. So sort of a more formal strategy pattern here, again, to give us, the UML. I mean, the basic idea we've covered here, which is right the right side of this, right? We have some sort of hierarchy here, a strategy here, like our sort, different sorts under it, for instance. Uh, but we want to actually apply those strategies to different objects. Okay, so this is the formal sort of strategy pattern here, where we think about what's the other object that we're going to make use of the patterns. Again, we can think about those examples like if I go back to the GIMP photo editor, where when I actually click on the cursor and do some action, I want to apply some strategy, right, for the different tools that's selected or whatever it may be. Okay, so that's the idea here. Okay, so a relatively simple algorithm here. So, I mean, let's look at strategy pattern in another game here. This will be the last sort of coding example. And disclaimer, I didn't work on this game project, but you could imagine how it might be used. Um, and let's say, I've got somebody scary like this orc here from Lord of the Rings for anyone who's a fan here. But, the basic idea is you have this structure here for this orc. And basically, what I want to do is be able to assign this, different orcs in particular as I instantiate these. Right, there could be one or hundreds of these in the game at a time. Different strategies for their combat. Okay, so maybe they, for whatever runtime behavior, they're not doing combat, or from a distance they're doing combat, or near somebody, whatever the reason might be. We want to have different sort of combat strategies where we could again change the behavior here. Okay, so this is the basic struct here, or the class. You could make it. And again, I have this combat strategy, and we're going to implement this interface for iCombat, okay, which is the right side of this URL diagram, which we've already done. Some inheritance structure that we can apply. And then all we really care about in this do actions, right, for our orc, which is going to go through, if it's an artificial intelligence, it's just going to process whatever the combat strategy is. It's just going to execute it. Okay, that's all it really needs to know how to do. It knows it has it. So again, we're doing some sort of composition here, and inserting into our context here, the orc, the different strategies. Okay, so that's basically all there is to it here. Now, we might have to think about some things, for instance, like how this strategy, for instance, maybe communicates if there are attributes in this orc, for instance, if it has uh, health or a power or a name or something that, it shouts before it does combat, how it communicates with this execute here, okay, this actual object here. So we could think about, for instance, um, passing in some arguments or populating this strategy. It could hold a reference to this object, and we might want to think about if that's a strong reference or just a weak reference. Right? We do have to think a little bit about ownership here, but that's a basic idea. And if folks have done other stuff with databases or in games, you could have a sort of component system where you can kind of look up the ID of this particular object and retrieve those attributes as well. So those would be some different ways to sort of handle this in a project. But basic idea is we're just using um, composition here with inheritance here to choose a different behavior or different strategy. Okay. So again, on the left side, that's the struct that we've previously looked at. On the right side here is our interface. Yeah, as mentioned in the comments, we've got the one orc to rule them all, just to get made them more powerful, maybe. But by default, we've got this strategy here for doing no combat. That's just what's set up when they are created. But we have some other ones that we can choose from: melee combat, range combat, and that'll do the appropriate behavior. Okay, and that's the basic idea. So again, we've got a family of related algorithms here. And I don't want to, again, in my sort of do actions for whatever the orc is, I don't want to do a bunch of stuff where I'm choosing state and saying, well, if the orc is this, if the orc is that, right? I could handle that somewhere else, but I want to keep this code relatively clean where I can just assign the strategy and then that'll be taken care of for me. Okay. Now, there are some different ways that we can pass the strategy into the orc as well, right? We could do this in the constructor if we wanted, but I want a little bit more um, control over this, right? So you could have a setter here for setting the strategy. We call that setter injection. Again, if we want to throw all these, fancy software engineering terms, those are the ones. But these are the different types of dependency injection, I guess, that we're having here, right? Where we're saying, okay, this is dependent on this strategy, so we got to implement something here. A setter function will do just fine here. There are other interesting ways that you could also set strategies. For instance, there is a service locator pattern, which is basically to say instead of setting this strategy explicitly, maybe we would request a service to see if it's available. So here, maybe there is some sort of global state here. That's one of the pros or cons of this service locator. You can look up and see based off some action that's happening in the game, and then populate these characters, right? Maybe this particular orc is very mad at you, so they um, you know have some behavior assigned in that manner. Okay, so just a few different ideas here. And then, of course, when it comes to using this, again, we get the same flexibility where we can create our object, do our actions, some time passes, we can set a new strategy. And again, when we perform our actions again, we will get a new behavior here, right? So now we're running away in fear, and then, soon enough, we're in range combat or something. Okay. And again, this makes it kind of interesting. Again, you wouldn't write this in your main. You'd have a loop or a game loop or something handling these actions. But again, hopefully it's obvious again that we can change the behaviors here. Okay. All right. So with that said, we've got about 4 minutes left. So I'm going to kind of start wrapping us up here with our summary. Just some pros and cons with the strategy pattern. Again, the strategy pattern is one that you can, think about or find in the wild, which is great to sort of study from. The pros and cons, as we've gone through, some of the pros being we get this ability to change behavior at runtime, and there's lots of different design patterns that allow us to change or extend behaviors at runtime. But again, the strategy is one of the cleanest, right? It's very simple, doing just inheritance and composition, essentially. But again, it's going to clean up your code a little bit if you could start wrapping things into objects or at the least functions, if you want to do a more functional approach. I'm going to argue again that this is going to probably give you more understandable code. That's been my experience with the strategy. Again, why it's one of my favorites. Again, if you're reading performance stuff, maybe you'll get everything into compile time where you're just setting the policies, and that might also be very useful. So again, the con, you need to measure your performance again because you are adding some layer of indirection, so just something to think about doing. And the fastest computation very well maybe just to do the one thing that you need to do, or as was mentioned earlier, if you just have four different use cases, maybe that's the fastest. So you just have to think about it and measure here. um, and the other con I could see is you might end up with just tons and tons of objects if you're not careful thinking about your inheritance hierarchy. So again, just something to be thinking about. So again, use the strategy pattern when you find yourself working with families of algorithms. Some of them will be very obvious, like sorts and searches, compression algorithms, traversals, and so on. If you find yourself with lots of if else conditions and switch statements, again, you want to think about ways to simplify your code, get everything into modular bits. That's usually beneficial. Again, you have to think about your use case. But in a very dynamic environment, like a game or something where you have to change runtime behavior, this could be a really useful pattern. And again, I'm going to argue for more testable code by wrapping things into objects and being able to prototype them. Yes, you can do this with functions as well. That's very well. But again, if you find yourself with lots of things that need to have a common interface, that might simplify or improve your testing quite a bit. Okay, folks. So, with that said, for folks who are attending this live, I'm going to meet you in the Gather Town. And otherwise, I'd just like to thank you for your participation and for listening in on this talk here now or in the future. And thank you again to C Online for hosting this wonderful conference and venue for us. And I'll hope to chat with you folks very soon. All right. Take care.